Hi. In the couple last videos, we've actually learned quite a lot about first-order difference equations. We learned how to solve them using iterative methods and, what is most important, general method. We also know how to deal with the cases when we have a variable coefficient using our favorite method of undetermined coefficients. Now, this knowledge that we've obtained actually opens a lot of doors for us. What do I mean by that? Well, if we look, first we deal with differential equations to be able to do mathematical models. Those mathematical models were supposed to tell us what is happening over time within given set of assumptions. However, once we moved to difference equations, I hope you see, on one hand, the connection between difference equation and time series econometrics, things that you already did in your econometrics class when you were analyzing time series like GDP, consumption, or investment. But now we know a lot more about different processes and how will they behave depending on what type of difference equation describes them. And look, this is where we are going now. Now, we're going to see how we can make economic conclusions about different variables. In 90% of the cases, we will be referring to real GDP, because this is the easiest, most intuitional one, definitely. However, you can apply it to different time series, especially values of stock indexes, or for prices of individual stocks. And look, if we are, why is this so important? Because look, if we, for example, find out that GDP or prices of stocks behave in a way that is similar to some of the types or one of the types of difference equations, we will be able to predict what is going to happen to GDP or prices if we know how to evaluate properties of this difference equation. Okay, and we're going to start by looking at two most commonly used stochastic processes in economics. But we're going to start with something simpler that actually is going to lead us towards what we want to have. Okay, and we're going to start with a process called random walk. Okay, process called random walk is given by the following difference equation. So, what do we have here? Here, we have delta yt, which we already defined, and this delta yt is equal to epsilon t. What is this epsilon t? Well, this is our shock. And look, we will be assuming that here we might have different positive or negative shocks. Where do we get that? Well, we will assume for the time being that they come from normal distributions with zero mean and variance sigma squared. Okay, what is this? Look, I think we discussed it before, but let's review it. Look, in the next videos, I will show you how exactly it looks on a computer, which is better in a sense that my drawings are not perfect. Computer does it way better. But let's start with the general idea. Okay, so imagine that we've got some probability distribution that is normal, and it has zero mean and standard deviation equal to sigma. Okay, so remember, this is the difference equation that is describing to us the pattern of changing y. Okay, and look, what might happen? You see that there is relatively high density of probability around zero, which means, for example, we can get negative shock, let's call it epsilon 0. Then you might have positive shock. There is less density over here, so there is very little probability that we can actually get a shock that would come somewhere from here, right? So what do we expect? We expect to have a lot of shocks, right? They're relatively close to zero, while the more, how to say, radical shocks, in the sense that they are taking relatively big or low, in a sense, very negative outcome, they are less probable. Okay, of course, again, as I mentioned before, it is better to see those drawn by a computer, but let me explain an idea of what is happening over here. Okay, imagine that here we have time, and here we have y of t. Now, what is happening over here? We are assuming that at each period from 0 to t, there is a random disturbance coming from the normal distribution with zero mean and standard deviation sigma that might happen. Look, in case of this equation, we will definitely be somewhere around zero. Because look, if not counting for these unexpected shocks, well, they can be expected, but a little bit about it later. This is a homogeneous equation, right? If I would like to start solving this equation, first thing I would do is I would do this. I would try a homogeneous version of that equation, right? And now let's see how it works. Look, I can already easily rewrite it into a form that is more convenient for us for solution. So, for example, this is the same as yt plus 1 minus yt equals to 0. And look, what is our a over here? Negative 1. Negative 1 is a special case that we've already discussed, right? And we know that in case with a equals negative 1, the solution, the time path, is given to some a, right? However, what is this a? Okay, look, first of all, we should notice that this A must contain information about what is happening within this system. Okay, look. We know that any difference equation can be solved by general method. And we already applied this general method to this specific equation, right? And what do we get out of it? A solution over here is only a complementary function, right? Because this is a homogeneous equation with weights. So the solution would be A times negative A to the power of t. But look, our negative A, if A is negative 1, our negative A is 1. So we see that we've got just A. But look, what was the interpretation of A? A is a deviation from equilibrium value. We clearly see that equilibrium value in this simple case is 0. Okay, but how does the disturbance term that we've introduced come into play over here? Look, it comes in a very specific way. Look, let's imagine that we start over here. Now, first, we have, let's just say, small positive shock. Then, we have, let's just say, let's start like here with small negative shock. Okay, so, what is going to happen? And as a result, we are below equilibrium. But then, what happens is, for example, we get positive shock that is bigger, as you see, than the negative shock. We would end up over here, right? Then we might have another small positive shock. We would get over here, but then we would expect to have small negative shock. Then maybe a bigger positive shock, maybe a bigger negative shock. Sometimes we might have, after that, we might have 2 more negative shocks, but we expect that after some time they will be compensated by some small positive shocks. What do I mean? Look, if mean value here is 0, we expect that if we add up all those shocks, they will be averaging out at zeros. We will have sometimes some positive shocks, sometimes some negative shocks. Right? And look what is happening. If I'm connecting those dots, I'm starting to have a picture like that. And look, if I would be drawing from this distribution more and more shocks, we would see that we will have something like that. This is why we call this process a random walk. What does it mean, a random walk? Look, imagine that it goes like this. We walk around the mean, but it's impossible to predict where we're gonna be. However, we can always say that we will stick somewhere around the mean, right? Because mean is at 0. So those shocks should be cancelling each other out after longer periods of time. Okay, but this should tell us one more thing. what is this A? Look, A that we've got over here is nothing more than the sum of all past shocks. Look, every shock that you got over here, that you get over here, stays in this A forever. So, because of that, all we do when we solve this and we have a constant, a new shock each next time period, the A has more and more elements. But remember, it doesn't mean that A is getting bigger. It can get bigger or lower for some period of time, but then it eventually reverts to the mean, and the mean is 0. So look, expected value of A at any t is 0. Because here is the line around which we fluctuate. But those fluctuations are completely random. And they all depend on shocks coming from this distribution. Okay. Now, I hope this is understandable. So, if we have a process where change in y at time t is equal to some specific shock, and the specific shock comes from normal distribution with 0 mean and constant variance, we would expect that the solution to our difference equation is simply a sum of all the past shocks. And look, because of this special construct, what we get is that A remembers is a collection of all the past shocks, which means A remembers every shock that happened over here, and this is why we call this type of process a process with perfect memory. Okay, but again, you might say like, okay, this is interesting. Yeah, this makes perfect sense. But this does not look like any data we've seen in economics, right? Because we very rarely have a situation when values are actually fluctuating around some constant or 0, right? We can find cases like that, but we rather see, like in the case of GDP, that we see secular growth. So GDP is generally growing, but rather fluctuates around some trend. And that is true. This is more like a purely introductory example, because the example that can be directly applied to what we know from economic theory is something a little bit different. And we're going to call it random walk with drift. Okay, so what is the random walk with drift? Okay, let's just start again by writing the equation that could produce. Okay. So, what has changed? I just added one tiny little detail to our first equation. What is this tiny little detail? This is alpha. So, let's think about this first. We will get back to this part a little bit later. Okay, now, if our difference equation would look like this, how do we read this expression? It generally says that each one period y increases exactly by alpha. However, we know that we can rewrite this in the following way, and we can use what we've already learned about difference equations. Remember, this is a special case where particular solution was found in a different way, right? And the particular solution to this case is simply yt equals to a. Remember, in case of this equation, this is the one of those cases where we cannot use a regular formula, right? So even though here we've got just a constant, what this equation produced is actually a differential equation with moving equilibrium. And again, remember that this is the particular solution, this is complementary function. So this part is showing to us what happens if we are in equilibrium. Here we see clearly that we've got a moving equilibrium. Well, this part is showing us what happens if we are thrown out of this equilibrium. And look, again, we have a equal to -1, right? And we already stated that negative, in this case, that in this case, what we get is the complementary function with b equal to exactly 1. So I hope you see the similarities between those two cases. Again, a have the same meaning. So a is simply the sum of all the past shocks, expected value of a at any time is 0, right? But in this case, what is the expected value of yt at any time t? Well, it is equal to alpha t. How do we graph this? Well, once I can put this on the graph, I hope you can start to see the merit in using these simple processes to model GDP or stock prices. Okay, so look. So this is value of y, and here is time. going to talk about perfect memory. Okay, so let's start with the trend. And look, in order to make this simpler, I will assume that y0 had some specific value at the beginning, and this is where we start. We do not discuss now how did I get this y0. I just want to avoid the situation where we start from 0 and I don't want to add here more components. I don't want to add here more components to make this equation more complicated. Okay, so first thing we should notice here is that we've got here time trend, right? So as time progresses by one period, value of yt increases by alpha. So you would have it like this. Of course, assuming that alpha is positive, which is a common assumption with economic time series. And look, in this case, it's not a problem to just draw a straight line through all these points, right? This is our moving equilibrium. This is our trend. Look, we call this type of trend a deterministic trend. What does it mean, deterministic trend? Deterministic means, in this case, that we can express this trend as a function of some variables. We can get this deterministic trend from some economic growth model, for example, an estimated, or like we did in this case, we are assuming that this is a simple function of time, linear function of time, and this is what we get. Now, the second thing we need to take into consideration here are shocks. And look, and let's see what we've got. We know that A, part of the solution, is simply a sum of all the past shocks, that on average, those shocks will be cancelling each other out, so expected value of A is 0, and if expected value of A is 0, then expected value of yt at given time t must be equal to trend value. Alright? So now how will this process work? Now we need to draw random shocks over here. But remember, when we do it, it goes like this. Let's call this point A1, this point A2. Okay, they should be, let's do it. Like, they should be exactly where are the yellow dots. Okay, so, first shock, A1. Then we've got another shock, A2. So we are moving to A2, then some another shock, A3. Then we have another shock, A4, another shock, let's just say A5, and another shock. We are at A6. Okay, let me illustrate what is happening over here. Let's just say that first shock is equal to -3. Okay, so A1 being sum of all the shocks from the past, okay, we're going to start from 1 till is plus 2, positive 2. Okay, what is A2? A2 is the sum with t starting with 1 until 2, t, which is equal to negative 3 plus 2 equals to negative 1. And look, this is what I mean by perfect memory. When we started, it's like you can think about it as the shock moved us over here. The second shock is a positive shock, right? It's plus 2, but it's not enough to bring us here. We are still negative 1 away. But look, continuing with this example, imagine that the shock number 3 is a big one. It's 5. What happens then? A3, which is the sum of all past shocks, is negative 3 plus 2, which is negative 1, plus 5, it gives us 4. And because of that, we end up over here. And look, this is what I mean by perfect memory. So A is simply a sum of all those shocks coming from normal distribution with zero mean and constant variance that we ever experienced over here. Okay, so if I now want to just draw a graph where I have this deterministic trend, I'm going to use this deterministic trend, and random shocks in case of random walk with drift, what I'm going to end up with is something that looks like that. So here is our trend, and around trend we move. Again, when I'm going to draw this to you on a computer, it looks way better. Okay, so what you see now is probably something that resembles things that you saw in your microeconomics class or in your finance class a little bit more. This kind of look like GDP, or maybe even some stock prices. Okay, so look, what we got from this is that we got a very simple model that we know how to solve easily. And because we know how to solve easily, we will know what kind of graph we will produce. However, the question is, what type of meaningful information we can get out of it? Look, let's just say you're working for a company that is supposed to predict stock prices. And let's just say the YT is the price of the stock that you are supposed to predict a value, let's just say 1 year from now. And let's just say that this data is daily. So, if this is the case, what is the best prediction you can give? If this is, let's just say, moment when you start predicting, and this is the moment where you should present, where you should make your prediction, what should be your prediction? Actually, in this case, your best guess is trend. Look, because there is no tendency to revert to mean, and there is tendency to move around the secular trend that we had over here, deterministic trend, we cannot tell where the price of this stock is going to be, whether it's going to be here or here or here or here. But the best predicator is actually the trend. And this is all you can get. You will not get any information about what is happening over here because those are random disturbances. They cancel each other out, so always your best guess is the trend volume. Okay, so this actually tells us that this might not be as informative as we might think. Like, all we can do is to estimate linear trend, and basically, this is it. Okay, however, as it turns out, the process you see over here, random walk with drift, is actually the best description of stock price movement we've got so far. Of course, we can assume that this is some autoregressive process. Okay, I don't want to complicate this too much. This tells us that we can only have some clue about the general tendency where the price of stock is coming, but we do not know where it's exactly going to be around this trend. And look, you might think about it as a bad thing, because it makes predictions harder. However, this is something what makes our stock market, equity market efficient. If somebody would be able to predict the stock prices perfectly, this person would probably start influencing this market. However, if other people notice this, started behaving similarly, this extra knowledge that this first person has disappears. And this is why, assuming that stock prices are random walks with drift, there is nobody that has better information than anybody else. So, even though it tells us that it's really hard to predict stock prices, it gives us also some indication of the efficiency of this, the efficiency of this stock market. Okay, but what about GDP? Look, GDP moves similarly to this, right? And actually, a lot of scientists believe that the, again, best model for GDP is random walk with drift. However, there is an alternative. An alternative is something we will consider now. The next type of process we're going to discuss is going to be called the trend stationary process. Okay. Okay, so again, we need to take some assumptions, and let's assume that yt plus 1 is equal to delta times yt plus some beta t, beta 1t plus alpha 1, and plus, of course, random disturbance, again, normal distribution, constant variance. Okay, again, this is the type of equation that we already know how to work with. However, before we make this equation a viable option for economic processes, let's make one additional assumption. And I'm going to assume that delta is somewhere between 0 and 1, which, when you will be doing your practical exercises, you will find out is what we find in the reality. Okay, now let's go through all the steps that we've taken before with our random walk and random walk quadrant. So first, let's get random disturbance out for now, and let's transform this equation into form that we know how to solve. So we can write it as yt plus 1 minus delta yt equals to beta 1t plus alpha y. What do we see over here? Well, we clearly see a difference equation with constant coefficient and variable term. Well, in order to solve it, what are we going to need is method of undetermined coefficient. But look, in this case, triad solution is very easy, right? You definitely try something in a form beta t plus alpha, right? Because this is a linear function, and consequently yt plus 1 is equal to beta t plus alpha plus beta, right? Remember, we substitute t plus 1 instead of t, and as a result, this is what we get. Okay, so first thing we're going to do is that we're going to find particular solution, so equilibrium solution for this case. Okay, so let's substitute. We get that this is beta t plus alpha plus beta minus gamma times beta t minus gamma times alpha, and it's equal to beta 1 t plus alpha 1. Now look, we can easily organize all of these expressions. We see that there are two expressions with t, so we get that this is 1 minus delta times beta times t, right? And the second one is going to be beta, and again those two can be combined to 1 minus delta times alpha plus beta. And this is equal to beta 1t plus alpha 1. Now, what we need to do over here is, of course, to find what is beta, what is alpha. Okay, so first we get that 1 minus delta beta t is equal to beta 1t. Right? Okay, we don't need t's. We get that beta is equal to beta 1 over 1 minus delta. And we know that we can calculate it because we assume that delta is between 0 and 1. So this is just expression, like assuming that beta 1 is positive, this is beta is just going to be better. Okay, so we've got the first part. Then we know that 1 minus delta alpha plus beta is equal to alpha 1, and we know that the beta is equal to beta 1 over 1 minus delta. So out of it, that 1 minus delta alpha is equal to alpha 1 minus beta 1 over 1 minus delta, and dividing through by 1 minus delta, we get that this is equal to alpha over 1 minus delta minus beta 1 over 1 minus delta squared. Okay, and look, based on that, we got that the particular solution, so equilibrium solution, for this difference equation looks like that. This is equal to beta times t plus alpha, or knowing, or simply beta 1 over 1 minus delta times t plus alpha 1 over 1 minus delta minus beta 1 over 1 minus delta squared. Okay. So here is our particular solution. So we know that, okay, for now I'm going to be referring to just this. This is a moving equilibrium in the format we know very well. And look, as we will talk later, this equation can be easily estimated. So look, if you estimate this equation, you will be able to get delta, beta 1, and alpha. So look, if you estimated beta 1, delta, and alpha 1, you will be able to get the particular solution. Okay, so next step, of course, is to calculate complementary function. Complementary function is a times negative a to the power of t. Right? What is our negative a? Well, I would say that this is minus delta. So we've got a times delta to the power of t. And look, now, for the first time, we've got complementary function that actually depends on t. Right? Remember, a that we had over here is where all our shocks are going. Right? If we have a shock, this random disturbance, our variable y is thrown out of the equilibrium by the size of the thing that we've got inside A, right? However, look at a very simple thing. Over here, if I calculate the limit with t approaching infinity out of A delta t, how much is it going to be? Assuming the delta is between 0 and 1, look, as time progresses, if this is 1 over 2, let's just say, well, it's usually 0.9, but let's just say this is 1 over 2, right? What are we going to have here? 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, 1 over until we get to 0, right? So you see, do we have perfect memory in here? Well, definitely not. Look, in this particular case, where we have transstationary process, if a shock happens is actually eliminated over time. Okay, so look, what we can get out of this is that the full solution, so time path of t, is given by a times delta to the power of t plus beta t plus alpha. And this, which you see over here, is the solution in the case when we have trans-stationary process. Okay. This trans-stationary, now let's draw how will this trans-stationary process work. Okay, so what do we have over here? We're going to start. Here we've got t, here we've got y. Okay. Let's forget about, for a second, about complementary function. Let's take to particular solution. We see that when t is 0, y is alpha, and from this point on, each time period, yt increases exactly by beta. So, we will have these constant increases, and again we will see a deterministic trend. Look, this is exactly the same type of deterministic trend that we saw in the case of random drift. However, we got it through completely different process, right? Still, we now also have a trend. So where do we see the difference? Okay, let's just say that at some point of time, let's just say t1, we have a shock. And GDP, let's just say that this is GDP, falls below equilibrium value. What's going to happen next period? Next period, of course, we follow trend. However, also the shock that we have here will be slowly eliminated, because look, our complementary function in this case will actually diminish the size of the shock. So we would expect that over time, the value of the serial of the deviation from equilibrium will be disappearing. Okay, I already showed you something very similar in the context of differential equations. However, here we've got, we are so close to working with actual data that I believe that this is something where we should put more attention. Okay, and now we can tell, okay, but this doesn't look like a GDP. If I was to actually show you just what I see in the data, it would look like this, right? Right? So if I would produce a graph that only show us what we observe, it would look like this. Drop, and moving closer and closer to equilibrium. And you might clearly say, yeah, but this is not how GDP look like. Definitely, GDP can never look like this. It would be weird, right? But remember one thing. Over here, happening every period, right? Our shocks come from normal distribution with constant variance and zero mean. So, actually, how this thing would work goes like this. Look, there is a shock. We're going back, but there's another shock. We're going back to equilibrium, but then there is a positive shock. We're going back to equilibrium, and let's just say that now there's a negative shock. And we're going back to equilibrium, but there's another negative shock. And we're going back to equilibrium. And look, what you would see as the outcome of that would be a line. Well, of course, remember we are talking about dots, but now you would see a business cycle. Fluctuations. That would look like this. Okay. Now, so based on what you just said, we will get a graph that looks really similar to random walk. In this case, why bother? Why cannot we just use random walk? Okay, look. Even though at the first time seen, they might look a little bit similar, when you think about it, they are very, very different. First thing that we already discussed is that in case of random walk with drift, we've got perfect memory. In case of trend stationary process, we don't. So what is the difference? Look, in this case, in case of random walk with drift, what you would see is that shocks going like that. Okay? Okay, I need to make dramatic differences. This is why it looks so weird, right? However, this is what we expect from random walk with drift. Over here, when we now have trend stationary process, we might actually have time trend that will look exactly like this one. Okay, I know you cannot see this in my graph because I draw this flatter, but for a reason. But let's assume that those are the same. Now, if I would draw the trend stationary process, what would be the difference? You would see that something that looks more like this. Okay, I hope you can see because I overproduced this effect. And here, we are getting further away from the trend, and it's definitely harder to predict actual value of y at any time. Here, however, the line looks a little bit more smoother, and it's definitely closer to the trend. Look, the entire secret behind this line being closer to trend is over here. Remember that in case of random walk with drift, we've got perfect memory. So here we have simply the sum of all the past shocks. In case of trend stationary process, this is no longer the case. We've got complementary function that is convergent. So imagine it like that. There are some market forces inside the economy described by this process that actually revert the economy to the trend value. For example, in case of GDP, every time when it deviates. And look, the difference between the two processes might not seem that big, but look at a couple of things. Where it is easier to predict actual value of y at some time in the future? Over here or over here? Well, I would guess over here, because there is this internal force that brings the values closer to trend. This is why actually distinguishing between different types of processes may be a key to finding an appropriate model. And look, another important thing that I want to mention to you is that in this case, once we estimate the model, we cannot say a lot about the speed of recovery of the economy if this is GDP, right? There is no force that actually brings GDP closer to the trend value. Over here, situation is different. Look, you can see actually that depending on the value we get on delta, we will be able to say how smooth and how close to the trend value we are. And remember that this delta can be estimated from the data. And look, again, let's notice a couple of things. Imagine that we've got three economies. Let's just say we've got economy number one, where delta is 0.99. Then we've got yellow economy, where delta is, let's just say, 0.5. And finally, we've got the economy where delta, without, of course, t, where delta is 0.1. Which of these three will get to the equilibrium the fastest? Of course, this one, right? Because we are taking the smallest number to the bigger and bigger power, so it gets very small very fast. However, in this case, the mean reversion or the trend reversion will be the slowest. So look, in the first case, we would expect the economy to look, let's just say, more like this, right? However, in this latter case, in the last case, the economy would probably be moving like this. So look, if we are able to estimate delta, we will be able to see how stable around the trend the economy is, right? And you can imagine that there are some economies where after being hit by a shock, they recover pretty quickly, right? But there might be some other economies that once hit with a shock, they suffer quite a lot. Okay, so knowing this, your next question should be, okay, so we know that a lot lot of economic and finance processes can be described either by random walk with drift or by time trend stationary process. But how should I know which one should I use? For that, we need to do some testing. And these tests, called unit root tests, are going to be the topic